Okay, so I restarted the stream in 1080p. Is that good? Yeah. Yes, yes, I'm here. Can everybody see this 1080p stream now? Okay. So, going back to the the topic from before, so to restart. Um, Basically, in C, you only have three different options to make memory allocation kind of flexible. One of them is to recompile the function definition. The other one is to recompile the function definition. And by that, we mean like changing some sort of a macro or something in the configuration header of a library. And the other one is to obviously link a different definition of memory allocation. And the third option, which is actually most commonly used, is to provide a allocator callback function. So, for example, your library, like for example zlib or lzma or png, or for example Vulkan, it would have a function signature for allocator callback, and the library says basically you can provide your own. But the main problem with that is that this is kind of runtime polymorphism done in C. So basically, you're asking for a random function pointer from the user, and you're going to basically dereference that pointer every single time. So this prevents stuff like inlining the custom allocation, like with static polymorphism, or optimizing across the function call. You cannot optimize, you cannot do any optimization across the site from where you call the allocation in that library and the polymorphic allocator. So, I mean, neither of the options is particularly good. So when C++ came around, they decided to use the template functionality of the language, to use templates and templated types to allow for statically polymorphic allocators. And this is what your STD allocator class is. So basically, the standard library, your C++, the C++ standard library that's provided with your compiler, with your runtime, that has a default allocator. It's called the STD allocator. And basically, it's a template class, which is able to allocate any number of objects of a specific type. And the way that they've envisioned the whole library is that every single container that needs to dynamically allocate memory, which is your vector, map, unordered map, list, linked list, everything like. Yeah, you've got a template parameter, which is for the allocator type. And the whole idea is that you get static polymorphism with those. So you can basically, at compile time, decide which allocator you're going to use. And the way that this was done in original C++ 03 and before is that the allocator that you used was solely defined by type. So it was more like a static class. And that was a huge problem because basically everything about the allocator, like which memory arena it allocates from, like where, where's the pool that it allocates from, everything like that was a function of its type. So it couldn't be like, okay, I'm going to have a class which is an allocator, and that basically defines the algorithm which we use to allocate memory. And then I instantiate multiple of these classes, and they will allocate the memories by themselves. It was more like of a hacky solution where the allocator basically could be constructed from the type, and you wouldn't be able to actually pass a specific instance of an allocator in there. So, like, let's say that you wanted to use an allocator that allocates memory from a specific memory area for let's say one would be for strings and another would be for vertices for your 3D object. In C++ 03, the way that this would actually work is that you would have to have a separate type for strings and a separate type for vertices. But then the problem was that basically in the original C++ 03 spec is that the allocators must be able to free each other's memory if they are the same type. So basically what that means is that, and this is still a thing in C++ 11, is that if you construct a new allocator, like a new object of the type allocator, it must be able to free the memory allocated with a different object of the same type. That's where the problem came. So it was actually impossible to do anything useful with these sorts of C++ 03 allocators because basically what it would mean is that as long as the type matches, you would be able to basically trade memory blocks around, So if you wanted a separate memory arena, which is basically what we call that, we've got one chunk of memory and want to allocate out of that. And then we've got another chunk of memory and we want to allocate out of that. And the memory arenas are separate. Then it would be really hard to do that. And one example where we might want to do that is when we've got threads, because an allocator will obviously have to, when you call allocate here, you can see the definition. When you call allocate, the thing is that this allocator needs to traverse some sort of a data structure to find a free area of memory, give you the best free area of memory that it can, and then return that to you. And the problem is that if you've got multiple threads, then not many data structures are thread safe, for reading and writing at the same time. So most of the time, what you'd have to do is basically make sure that only one thread goes into this allocation function at a time. You have to put a mutex around it, like an exclusive critical section, to make sure that the allocator is only being called by one thread at a time. And this doesn't scale very well when you're when you're running a lot of threads and doing a lot of allocations. So one way to solve that is to have a per thread pool. And this is what this library called tcmalloc does. So basically you have a separate heap of memory per thread. And most of the time, this allocation function will only go within the thread's own little pool. And if it finds the memory within the own thread's little pool, then you'll never have to issue a mutex and have like an exclusive lock for execution. You don't have to block any other thread. But obviously in the rare case that you cannot find any memory in the thread local pool, you have to get some more from the global pool. And that obviously requires a mutex, but that happens very, very, very infrequently. And the main problem with those C++ 03 allocators is that to implement this sort of system, you'd have to have a separate type for every thread. So you've got your STD allocator and so on. You'd have to make a special new class that is just a new class with a new type for just so you can have one more thread. Or the other solution would be to, So basically, I can show you in Visual Studio what that would look like. So I'm gonna just change over to Visual Studio. So I'm just going to start a new file. Actually, I'm just going to write on the end of this one. Okay. So the main problem is that if you've got a STL allocator and some type, let's say float, and if you have any kind of class that uses it, like for example a vector like this, there's a vector float that's allocating from STL allocator. The problem is that so the problem is that if you do this and you resize it to, let's say, 1,000 floats, then technically speaking, right? This is obviously not very portable behavior, but you could do something like this. Technically. Like, this is a behavior that C++03 would support. Because basically is like, as long as the type matches, the allocators can free each other's memory. So, without further ado, I'm going to show you which is something that's perfectly legal in C++03. And somewhat still in C++11. So your allocator, if you want the allocator to be compatible with the standard template library allocator, so if you want to write an allocator which does this by itself and can be used by a vector or any sort of other container from a standard library, then your allocator needs to support this sort of behavior. So it's 100 floats, and int is not given. I'm just gonna have to look up the definition. Yeah, okay. This sort of behavior is 100% legal in C++03. And 100% required. So basically the main problem is that the problem with that behavior is that you cannot achieve what's called polymorphic allocation, which basically means that depending on the allocator instance that you give to a function, then this allocator instance will actually allocate from a different memory pool. So basically what this means is that your allocate and deallocate functions, even though they might not be static, like static functions in C++, they would have to make use of static data members. So the only way that this is going to work we'll go again? Yes? Say that again. Basically, the idea was with C++03 is that the container that you're going to use doesn't even let you pass a specific instance of the allocator. In C++03, it would only take this type here, whatever type you're going to give it, just let's do float again. My custom allocator, yeah, Yeah. And the main thing is that the constructor for your for your container would never allow you to pass in one of these instances. The container would always create its own instance inside the constructor. So somewhere inside the constructor, you would have you'd basically have this. In C++03. So basically, because this would happen, you basically have to have an allocator which basically is static, like 100% static. Like every single allocation would be global, doesn't matter which instance of the allocator does it, and so on. Like you wouldn't be able to pass any information to the allocation function of the allocator. And thankfully, in C++11, so thankfully in C++11, they introduced this thing called stateless allocators. So stateful allocators. So this is a stateless allocator. It has no state. Except for system state. Like you can still hack this allocator to work with like different threads, because you can, even if you're a function that you don't know where you are, or if you're in a static function, you can still get the thread ID from the system. But basically, this allocator could not contain any state whatsoever. And a great way to show you an allocator that's stateless is allocator. Yeah, this is the aligned allocator from our engine. So you can see that here you've got basically the type, and this is an extra parameter that the standard, the STD allocator does not take, but it's default, so it will work even with things that are designed to use the standard template allocator, because you can just give the type and it doesn't need to worry about this parameter. So this is the aligned allocator, and this is a C++11 allocator. So this is a little bit less of boilerplate to write. There's a lot less code that you need to write to make it work, because with the C++03, you would have to redeclare a lot of like variables like this, like lots of type defs and stuff like that. But thanks to C++11, we only need to write about this much code to make it work. So basically, this is a stateless allocator. So as you can see, this allocate function here, I could make that static if I wanted to, because it gives you back the pointer. It takes the number of elements to allocate, their alignment and the hint. And see, here there's nothing that actually, there's no state. See, there's no local member variables, nothing. It has no member variables, so basically doesn't matter what instance it is, it always does the same thing. Like here, it just calls a global function called aligned malloc, which is basically just a wrapper here. It's just a global function call, and the allocation is the same. So essentially, this has no state, no member variables whatsoever, and basically a different instance, a different object of this type can deallocate the different objects allocations. And this sort of allocator would be like almost okay to use for C++03. Any questions so far? Well, okay. I think there is no difference here, really, except that this would be pretty much almost like your standard libraries allocator, declare, except for this here wouldn't be an aligned malloc or an aligned free. It would actually be a malloc and a free. This is exactly the same as your normal kind of standard library allocator, except that it gives aligned memory. Because basically this is an extra function here, that's extra, and this is also extra. Only these two, this and that, these two, only these two exist in a standard template library allocator. So it's an allocate, how many, and a hint, which most of the time doesn't mean anything. It's a hint specific to an allocator. And the allocate takes the pointer and the number of elements which are allocated at that pointer. And here you usually have like a malloc or a global new, and here you have a free or a global delete. And that's all that your vanilla allocator does. Obviously, in your standard library, there might be with this particular allocator, no. Yeah, so now I'm explaining C++03, which was the old revision of C++. And this is the allocator that pretty much conforms to C++03. Stateless. All allocators for C++03 need to be stateless. So one object of this type needs to be able to manage another objects of this type memory. And with C++11, you have stateful allocators, which still do not allow for 100% polymorphic behavior, but it's close. You can actually use them as a workaround to get polymorphic behavior into the allocator. Because for polymorphic behavior, as you will see, you will actually need a state in the allocator. Because if you have runtime polymorphism, so if the function that you are going to call to allocate will be different under different runtime conditions, then this requires a state. And the easiest way to get polymorphism into an allocator like this would be to replace this with a call to a function pointer and replace this with a call to a function pointer. But you need to store the function pointer somewhere. And that would need to be a member variable in this allocator. So this allocator would have to have a state. It would have to be stateful, not stateless. If you get what I mean. That does that, yes. Yes, exactly. Yeah. And yeah, exactly. So C++11 brings us to stateful allocators. So this was the definition of allocate. Obviously, in our engine, Ilicba, we do not support exceptions. Exceptions are confusing. So we don't throw anything, and we don't also check for exceptions or anything like that. We would compile without exception support if it wasn't for the fact that several of our dependencies actually do throw exceptions, and we can't compile without exceptions that easily, especially SPIR-V cross. But generally speaking, we don't want to use exceptions. So, so the C++11 allocator This was the all custom allocators also must be stateless. That was until C++11. And as I've mentioned, the default allocator is stateless. All instances of the given allocator are interchangeable. They compare equal and can deallocate memory allocated by any other instance of the same allocator type. So that's about the default allocator. Now, since C++11, custom allocators may contain state. Each container or another allocator or object stores an instance of the supplied allocator. So before, when you had a C++03 vector or map or list, that object would not actually store a member of type allocator. Every single time it actually wanted to allocate memory, it would call a constructor on the allocator type, get itself like a temporary object of allocator type, and call like allocate and construct, and then this allocator object would die. And when it would actually deallocate, it would make another temporary object of class allocator to do the deallocation and the destruction. So you can see how like insane that was. And this is the interesting part, is that each container or another allocator, our object now, it stores an instance of the supplied allocator. So now when you, in C++11, when you actually do instantiate a vector or a map or a list, then it would actually have an instance that it constructed, or an instance that was moved as well, because you can have move constructors on allocators. Basically, this allocator would live as long as the object, the container. And because it would live as long as the container, it would actually be allowed to keep some state that would be preserved between all different allocations and deallocations. But the problem is still that there's no ref counting in C++, except for obviously shared point or anything like that. So the allocator actually needs to be copied with all of the state. So for example, an allocator, one thing that an allocator in C++11 cannot do right now is create a memory pool in the constructor and destroy the memory pool in the destructor. Because like when the container that uses the allocator has the destruct, it also needs to destruct the allocator that it's using internally. So one thing to take away from this is that the allocator does not, the particular instance of the allocator does not equal the allocator, the memory pool itself. So the instance of the allocator cannot be the memory pool as well. So the allocator is allowed state. So a C++11 stateful allocator, it can contain a reference to a memory pool, but it cannot be the memory pool, because otherwise this whole thing is not going to work, because there's too many destructors being thrown around. And also the allocator will need to be copied, needs to be able to be copied with the state. The state will also be copied. So basically an allocator is allowed to be something like a shared pointer to a memory arena that it's allocating from, like an actual thing that does the allocations, but it's not allowed to be the thing that the allocations actually take place from. Because otherwise, even with C++11, that's going to break. So obviously you can see that in order to be usable by the containers, needs to be a few definitions of members and some constants, like always equal, propagating container move, and so on and so on. And in C++, the allocator also handles the construction and the destruction, which is a bit weird for me. I don't particularly like this, but that's what it does. It actually handles the construction, destructions of array of objects. It like actually goes in and calls the constructor multiple times, like in place. But thankfully, to a class called allocator traits, this thing here, Allocated traits is actually able to deduce a lot of those things. Allocated traits, for example, is able to deduce most of those. It's able to deduce constructor and the construct and destroy, which have been removed in C++20. They did finally see how weird that is. And a few other things. So now actually, thanks to allocated traits, because the containers that you use in C++11, they actually rebind the allocator through allocated traits, which is really weird, but it actually it makes a lot of sense. And thanks to that, in order to declare a working C++11 allocator, you only need to declare allocate in the allocate, really. And the very interesting thing used to be, now it's removed in C++20, I don't know what reason, is the equals and not equals operator. And this actually has a very important meaning in C++11 to 17. Basically, the sort of behavior that I showed you here, where, for example, allocator instance B would be able to deallocate the allocator instance A allocations. That can still happen in C++11, but it will only happen if this is true. So if the two allocators compare equal in C++11, so in C++11, if the two allocators compare equal, one allocator can deallocate the other allocator's memory. And if we go back to my aligned allocator, you can see that they always compare true. No matter which two instances, even if the types are different, like even if you've got an allocator for ints and an allocator for floats, they will always compare true, and that means that they can always remove each other's memory. And that's well, it's not bypassing anything. It's just well, yeah, I always return true just so, because this little allocator here is supposed to be exactly the same like the standard allocator, except that it's giving you aligned memory. Because here you can see that there's a template argument extra which says over align, and this is a constant expression, static constant expression. And basically, if you don't provide, like here you can see there's no alignment. So if you don't provide an alignment, it will always allocate memory with the default alignment or whatever alignment you have in the type. And if you do actually use a different API, which actually knows about this alignment parameter, and mind you, this is going to be none of the standard library containers will use this function. Only we would be using this function, because this is an extra function that I made. This is an extra function. This is the function that C++ actually requires from my allocator. This is an extra function. And here, if you actually did give it the alignment, it would actually give you memory aligned to a certain alignment. And by alignment, we mean a pointer to memory, which, like when you convert to a number, is divisible by the alignment. So most of the time, we want to have pointers aligned to 16 bytes for SSE, streaming extensions. So basically, when you have a pointer, it's not actually a good pointer. But basically, if it's aligned to 16 bytes, then it always has a 0 on the end, because it's divisible by 16. This is actually default in 64-bit systems now. So the malloc and free will give you that by default. But there's an extension for processes called AVX and AVX2 and AVX 512, and these require 32-byte aligned allocations. and so on and so on. So this is basically why I made this allocator. It's just to make sure that if you want aligned memory, if you do need aligned memory for a type in a, for example, in a vector or something like that, then you will actually get that aligned type. Because, for example, some of the classes in the engine, like for vector 3df, vector simdef, that one, this will actually crash the engine if you have a pointer to it, or if you construct it, or if you try and use it at an address which is not aligned to 16 bytes. And this is because it uses SSE2. And if we made a vector, for example, we've got, so yeah, this is like vector 4df, but if we made an vector 8df with AVX, then this would have to be aligned to 32 bytes. Or if for example, because Chris did some benchmarks with AVX, so we've got another type called matrix 3x4 by SIMD is actually not a good example, but we've got the matrix 4 SIMD type. So this one occupies 64 bytes, and it's made of 4 SIMD SSE rows. And we could actually pack that into 2 AVX 8E registers. And what that would mean is that this whole type would need to be aligned to 32 bytes. So this is why it's so important to care about memory alignment, and even more when you go into stuff like Vulkan, when it's alignment starts to matter a lot. So this is basically to make sure that you can make a not undefined behavior. The x86 CPUs are very good at detecting unaligned loads. So the program will actually crash, and you'll get like a CPU hardware exception. Because it's all about, there's a intrinsic, there's a thing called load PS, and that requires an aligned, you can see, takes a pointer, and this pointer needs to be aligned. Because otherwise, whatever code issues this instruction will crash badly. And it's the same for AVX. And it's even worse for example, for ARM, because in ARM, if you use a lot of byte arithmetic, you cannot, for example, cast an unsigned byte pointer or a char pointer to an int pointer, unless the pointer that you're casting is aligned. If it's not aligned, then the ARM CPU will crash. It cannot handle unaligned loads. So yeah, so anyway, this is our allocator, which conforms to the standard allocator. It's C++11, it's written like C++11, but it obviously does always compare true to another instance of its type. Just because I wanted to keep to that convention. And obviously it inherits from the allocated trivial base. And the allocated trivial base, it doesn't do anything much except for one very important thing. It declares all of the silly aliases for all of the type defs, value type, pointer, const pointer, reference, construction, all of that stupid stuff. It declares, just so it's there. So this is our aligned allocator. And now I will show you. Now I will show you a different allocator, which is exactly the same as the other one, but it has a slightly different purpose. It's called the null allocator. And the null allocator, we have it just for fun. It's actually an allocator that doesn't do anything. Like some code can still call it and try and allocate stuff, but it's not doing anything. Like it's not allocating any memory, it's not doing anything. You know, here it's just not. There is a good reason why I was using it, and I can search for usages of it. Oh yeah, yes. It's because our CPU buffer, by default, you make it the default class, which implements the CPU buffer. It just allocates the data pointer, the internal storage of the buffer, through just a malloc and a free. But there's also a version, which is the custom allocator CPU buffer, which can allocate the buffer storage through an allocator. So you can see here how it's almost exactly the same like a container object, like a vector in a use of the allocator. So here you've got an allocator which you can pass in. If you don't pass one in, then the default will be made, but you already know the type. And this allocator here gets moved into this allocator here. And this is the allocator which is, you know, an object of allocator that's kept alive for the duration of the lifetime of the buffer. And then the buffer actually uses this little allocator to allocate the memory. It allocates the memory and it also deallocates the memory using this allocator. And the most interesting thing, like here you can see where it's actually using it to allocate the memory. And this is the specialization for the null, see? And the reason why we did it like this is that you can use the null allocator on this buffer here if you only want the buffer to be a view onto some memory. This is this is a buffer that you can create a buffer over some already existing memory. Like, let's say the memory, the engine has only APIs which take an iCPU buffer as input of data. Yeah, like for example, the new stuff in the API is like specialization constants for your shader. You know, if you don't want to be stupid and make a new buffer with malloc and so on, just so you can feed some simple constants into the shader compiler, or if you already have some data in some memory, then you can use these custom allocator buffers. So then, for example, if you use a custom allocator CPU buffer with the null allocator type, then you can create the custom allocator CPU buffer over the data, and the allocator will never free it. So you can basically have a view onto some already existing memory through this custom allocator CPU buffer as an iCPU buffer that you can then pass into all the functions. But this particular derivation of iCPU buffer will actually never own the memory. So it can be just like a window into the memory. It's not taking ownership of it. Yeah, so this is basically the only reason why I made the null allocator. Because otherwise, if I didn't make the null allocator, then I'd have to have one special class to make a buffer with an allocator, and one special class for a view into a buffer that doesn't actually allocate and doesn't own the memory. But here I could just do it with one class, with one template class. Just not to be weird about it. So anyway, this is another way that you can overload a C++ allocator. And this, my friend, is a polymorphic allocator. Actually, this in itself, yeah, this does not make the allocator compatible with a container. Just saying. So basically, this is something similar to an allocator. This is just an allocator that has virtual functions that you can override. But this will not work with the standard library, because the standard library expects an allocator with a particular type, and so on and so on and so on. So actually, what we have here is an adapter. So the way that this works is actually pretty funny. Is here you can make a polymorphic allocator, which depending on the type of the instance and so on, has all of the virtual table and everything like that. So we can call a different allocate and different deallocate function at runtime. You can just swap them out at runtime. But it requires an allocator adapter to kind of like wrap it. It's wrapping around the type, so you'll only be using that one. And what this little baby does is it inherits from an allocator that you're going to pass into it, like an allocator type, but it's also of the instance of this ally allocator. And it will keep a reference inside of itself. This is like a weird notation, but because it inherits from this allocator, the state of the allocator is already inside. So this gets the state base ref, and then it's using the base reference to allocate, and a base reference to deallocate. And this is a stateful allocator. So basically, it will not compare equal unless the underlying classes compare equal. So this is basically a stateful allocator. And you can actually shove different allocators inside. Pretty much. Yes, exactly. Yeah. And yeah. And this is basically how this whole thing works. But this notion of allocators is very limited, because in C++ they can only give you pointers. They can only give you pointers to actual memory that's visible to the CPU that you can actually use, read and write to. But the problem is that, for example, in Vulkan, you're only allowed to have about 4,000 device memory objects, and you need to like allocate offsets from the start of the memory object. Or, for example, if you're trying to do virtual texturing, then you have one big texture, and you're trying to allocate like squares out of it. Like, here's your big texture that's, for example, like a light map or a texture atlas, and you need to allocate, like, for example, like something this size. So then you got to figure out, like where to put it in the texture, yeah? And then you get another one which is like this size, and you got to figure out where to put it, in the texture, like here, or something like that. So this is also like an allocation problem. So, or for example, if you need to just allocate IDs in an array, like, let's say this is like a standard library problem, not a library problem, standard like shader rendering problem, is that, in a shader you've got, for example, a struct called, I don't know, object, and you've got, your color, and then you've got your don't know, world view projection matrix for the instance. And then some other stuff. And then you've got yourself a little buffer, which you call instances. And for the shader to work, this whole thing has to sit in one buffer. And let's say you want to draw multiple objects using these buffer and this buffer. So then you do like instance, just object. So object and current, and then you're trying to get this thing, and then you're trying to get it from this little buffer using some sort of an ID. Yeah. What's that gonna be? You obviously you can try to use GL draw ID. You can use GL instance ID, but those are only relative to the current draw that you're executing. Like if you're gonna throw some culling into that, or not draw a few things, or maybe do some other stuff like that, then you need to have a unique ID for the object. And with this, you need an allocator to give you this unique ID, because when you're adding and removing objects from the game at runtime or from the scene, then you need to think up of an ID, like just a number that hasn't been used before, that's not in use, that hasn't been given to a different object. And then when this object wishes to be destroyed, then you need to return this ID to the already given ID pool to be reused for the next object. And this is all of this comes down to just allocation. All of those problems, allocating memory to use for objects in a container, allocating those unique numerical IDs also comes down to allocation, and allocating texture space in a texture atlas also comes down to allocation of this sort. Everything like that, all of this, it comes into just allocation. And all of these problems can be solved with allocators that just return numbers. They don't return memory addresses. You don't need the memory to be present there. You just need to return numbers that hasn't been used, just number ranges. And that's what we're going to talk about next, which is basically address allocators. And that's basically what the rest of the engine. Numbers, those are basically just just unique number ranges. And then if you want to allocate memory, you can just turn those numbers into pointers by adding them to an address. That's all there is to it, really. But there's nothing more, because all our memory allocator does is just like a C++ allocator. It thinks of a number. No, okay, so basically, okay, so I think we should take a break, and I can go into this after the break. Okay? All right, so I'm gonna take a break for 5 minutes, and we'll be back.